guys, welcome to my first chemistry review. Today's video is going to be about Unit 1, specifically lessons 1 to 5. So let's get started with lesson 1.1, which is lab safety and equipment. And the goals of this lesson are to recognize lab equipment and safety equipment. So we're going to start off with a little interactive quizzing. Name the lab equipment that you see on the screen. Okay, so I'll give you a few seconds to read through your options here and decide which one best describes the image on the screen. I'll count down from 3, but if you need more time, pause the video. Okay, 3, 2, 1. This is a hot plate. Next one. 3, 2, 1. This is a beaker. Next, 3, 2, 1. This is a Erlenmeyer flask. Next one, 3, 2, 1. This is a pipette. Next, 3, 2, 1. It's an electronic balance. You guys have already seen these. Next, 3, 2, 1. Spatula. This one, 3, 2, 1. A plastic sample bottle. This one is very important. 3, 2, 1. This is a graduated cylinder, and I would definitely get familiar with these because you will be seeing them a lot throughout the year to take measurements. And then I think this last one. 3, 2, 1. A weigh boat. Okay, so next quiz. Safety equipment. Which image, the left or the right, shows the fume hood? 3, 2, 1 would be the left. On the right, it's a broken glass bin. Next, which is the eye wash? Is it on the left or on the right? 3, 2, 1. It's on the left. On the right, we have the safety shower. And then here's just a list of the journal equipment you should know. Let me move myself. All right, never mind. Okay, lesson 1.2 is about data collection and analysis. So what do we do with the data we collect? How do we decipher it and make meaning of it and analyze it correctly? So first, we are looking for accuracy. But what are we looking for when determining accuracy? Are we looking for how close a measurement is to the accepted value, or how exact a measurement or a series of measurements is? The top, how close a measurement is to the accepted value. And on the bottom, I don't know if you can see, move myself. So calculating accuracy. So we calculate accuracy by finding the percent error. So here's the equation for percent error. It's the experimental value. It's the absolute value of the experimental value minus the accepted value divided by the absolute value of the accepted value, and then times 100% to make it a percent. And what experimental value means is it's the value that is found in a specific lab or analysis, something that you find yourself. And an accepted value is more of the general value that tends to be, what it is. And how do we interpret the percent error that we calculate? Well, the smaller the percent error is, the more accurate the measurement is. So, for example, if we found a percent error of 6 compared to another measurement that has a percent error of 20, the measurement with the percent error of 6 would be the more accurate one of the two because it has the smaller percent error. Precision. So precision is how exact a measurement or a series of measurement is, and it's measured with range, which you've definitely seen in math before. In terms of chem, it's the same thing. It's just the difference between your highest value and your lowest value. That's your range. And the smaller the range, the more precise a measurement is. So, for example, if the range was from 8 to 10 versus 2 to 20, the 8 to 10 is a smaller range, so that series of measurements would be more precise. Okay, and if you're like me, you like more visual models. So this isn't necessarily something you're going to be tested on, but I thought it was a good way to kind of think about it. Accuracy versus precision. So we have 4 targets here, and out of these 4, which ones go with A, B, C, and D in terms of the little dots on the target? I'll give you a few seconds to think about it, and then you can pause if you need more time. Okay, 3, 2, 1. Here we go. So number 1 is A, which is high accuracy and high precision. As we can see, the dots are accurate. They are close to the center of the target where you would want them to be. And they have high precision because the points are all within a small range to each other. Compared to number 2, which is C, low accuracy and high precision. So it has low accuracy because it's not on target. See, it's more skewed up here. However, it has high precision because the points are all close together, so small range, high precision. And then number 3 would be B, high accuracy, low precision. So the points are all pretty much on target, but they are pretty spread out, so not very precise, has a bigger range. And then finally 4 is D, low accuracy, low precision. So not only are the points not on target, but they also are very spread out. So not accurate and not precise. Okay, make myself over here. Making precise measurements. So for making precise measurements, we want to estimate 1 digit beyond what the markings of that tool provide. So we have an example of that here. So you can see ruler A, they provide the markings of the 10th place of the decimal, because between 2 and 3, there's 1, 2, 3, 4, 5, 6, 7, 8, and 10 markings. So how we would want to assess this measurement is, let's say it was right here at the blue line. So we can see that it falls in between the 5th marking and the 6th marking. So we would want to estimate 1 digit beyond what the markings provide. So if the markings provide 2.5, since it's the 5th one, or 2.6, whichever one you would want, we would go 1 digit beyond that. So we would do 2.55. As we can see, this blue line kind of falls right in between 5 and 6, so 2.55. Now for B, there's one less value, or I don't know how to describe that, like marking, than ruler A. It only has 1, 2, 3, not the little tenths places in between that. So we would only have to go to the 10th place of the decimal point for our estimate. And we can see that, again, it's kind of right in the middle of 2 and 3, so a good number to estimate would be 5, so 2.5. Okay. Significant figures. This is a really, really important topic because it's going to follow you throughout the year. They never go away. So what makes a number significant? So significant numbers are numbers that carry meaning. Numbers 1 to 9 are always going to be significant in every number. And where it gets tricky, and where I had a lot of trouble last year, is when it comes to zeros. So okay, I'm back. I figured out how to move myself out of the problem. Okay, so rules for zeros. Number 1 is if it's sandwiched in between 2 non-zero numbers, then it is significant. So, for example, 4.608, since that 0 is in between a 6 and an 8, 2 non-zero numbers, that would make it significant. Rule number 2, if a 0 is at the end of the number, but it's after a decimal point, then it is significant. So like 2.10, that 0 ends the number, but because it's after the decimal point, it is significant. However, if a 0 ends a number before the decimal point, it is not significant. For example, in the number 100, there are 3 digits, but the last 2 zeros are not significant because they are ending the number before a decimal point. And remember, 4 zeros that start a number are not significant. So like 0.37, that 0 starts the number, so it is not significant. Okay. Now, let's see. This number here is 0.0560. How many significant figures are there? I'll give you 3 seconds, but if you need more time, you can always pause the video. 3, 2, 1. There are 3 significant figures in this number. The first 2 zeros, this one and this one, the red ones, they are not significant because they are leading zeros. But the last 3, 5 and 6, are non-zero numbers, so they will always be significant. And this 0 is an ending 0 after a decimal point, so it is significant. So 3 significant figures total. Okay, next one. Give you some time, you can pause it. 3, 2, 1. Okay, the first 3 zeros, again, are leading zeros. They are not significant. But the rest of the number is significant, these 5 here. 5, 8, 3, always significant. This 0 here, hope you can see my cursor, I'm gonna have to watch this back, but the 0 between the 5 and the 8 is sandwiched between 2 non-zero numbers, making it significant. And then this 0 at the end is at the end, but after decimal point, so it is significant. So this would be 5 sig figs. Next one, 3, 2, 1. Okay, this one, they are all significant. The non-zero is always significant, and then the zeros are sandwiched in between, so they're also significant. So 6 sig figs for this one. Okay, this is a wordy slide, I'm sorry. Calculating with sig figs. So there's a difference when you're adding and subtracting sig figs versus when you're multiplying and dividing them. So for adding and subtracting, it's going to be the same kind of rule. So you want to add or subtract all the numbers using all of their digits. So that means not rounding them early, only rounding it at the end. And then at the end, you want to round the last place that is significant and common to all values. That might be kind of hard to interpret, but there will be an example, but that's how you would put it into words. For multiplying and dividing, you want to multiply and divide your numbers, again, using all of the digits, not rounding early. And then you want to round your answer to have as many significant figures as the value with the fewest significant figures. Okay, I think it's easier to see it in an actual problem. So for subtracting, take a second, pause the video, try this out. Subtract this number from this number using our sig fig values from the other slide. Okay. I'll show it in 3, 2, 1. Okay. Okay, so for this one you would want to subtract the numbers normally as you would, and then you're left with 3.2381. Now, when you're thinking about how to round this, you look at the numbers place that is significant and common to all of them. So in this one, this has 4 decimal places, this one has 2, so they both have this second decimal place in common. So then you would round the answer also to the second decimal place. And since it ends in an 8, you want to round this 3 up to a 4. So your answer using sig fig rules would be 3.24. Okay. Multiplying, it's a different kind of rule, so make sure you know what rule you're using. Okay, I'll show it in 3, 2, 1. Okay. So for this one, it's whichever number has the lowest amount of significant figures, you would base the answer off of that. So the first number has 3, the second has 4, so the last number should also have 3, as it's the lowest amount of significant